First, all reference equations will be found in Fundamentals of Engineering Thermodynamics, 7th edition by Morin and Shapiro. Problem 9.6. A four-cylinder, four-stroke internal combustion engine operates at 2800 RPM. The process within each cylinder are modeled as an air standard Otto cycle with a pressure of 14.7 pound-foot per inch squared, a temperature of 80 degrees Fahrenheit, and a volume of 0.0196 cubic feet at the beginning of compression. The compression ratio is 10, and the maximum pressure in the cycle is 1080 pound-force per inch squared. Determine using a cold air standard analysis with K equals 1.4 the power developed by the engine in horsepower and the mean effective pressure in pound-force per inch squared. Now let's begin by writing out all information given in the problem, which I've already taken care of. As stated in the problem before, it's just written out a little bit easier. Due to it being modeled after an Otto cycle, we know that processes 1 to 2 and 3 to 4 are isentropic, compression, and expansion respectively. These are better shown in a PV diagram. As you can see above, I'll zoom in on it a little bit here. Here's your PV diagram. You can see in which states isentropically they're shifting. And if anyone is interested to know, this is actually the drawing or a diagram of a inline four-cylinder engine. To find T2, simply use equation 9.6. As seen below, you can see that T2 divided by T1 equals V1 divided by V2 to the K minus 1. Now all we're going to do is input our known values and do a little bit of math. As we know, the V1 divided by V2 is our compression, so that is equal to 10. Our K is 1.4, and our T1 is 540 degrees Rankine. As you do your math through there, it should come out to 1,356.42 degrees Rankine. Now as we scroll down, to find pressure at state 2, simply use equation 6.43. As you can see here, P2 divided by P1 equals V1 divided by V2 to the K. So we'll simply do the same as we did for the temperature at state 2. We'll input our values. V1 divided by V2 is equal to 10. And as you see, you multiply across and you get 369.2 pounds per inch squared. Finding T3 is a relationship comparison. It's easier seen with the PV graph. As you can see, V3 is equal to V2 on that graph. So we'll simply set up P3V3 divided by T3 is equal to P2V2 divided by T2. As we input our known values that we have already found and already have been given in our initial problem, you set it up as 1,080 pounds per square inch divided by 369.2 pounds per square inch times 1,356.42 degrees Rankine, which gives you an ending value of T3 is equal to 3,967.86 degrees Rankine. Finally, to find T4, we will use equation 9.6 again. Do note from our PV diagram the following comparisons. V3 is equal to V2 and V4 is equal to V1. V1 divided by V2 is equal to 10, while V3 divided by V4 is also equal to V2 divided by V1, which is equal to 1/10. Now, as we plug in our known values into our equation, T4 divided by T3 is equal to V3 divided by V4 to the K minus 1. We input these known comparison values, and you get T4 is equal to 3,967.86 degrees Rankine times 1/10 to the 1.4 minus 1, which, as you multiply out, will give you 1,579.63 degrees Rankine. Our last calculation is of the mass of air by the ideal gas equation, 3.33. M equals PV divided by RT. Now I'll be using this as a state 1 since we have all of those known values. The R is the universal gas constant, and as you can see in the equation, we went ahead and input our values. The only value that you might not have is the R, which in our case you can see is 1,545 divided by 28.97 foot-pounds per pound degree Rankine. 28.97, do note, is the molar mass of air. As you multiply across, you get the mass of air is equal to 0.00144 pounds. Now that we are done finding needed values, let's find the work of the cycle. For this, we will use equation 3.47b, volumetric heat capacity, CV, and equation 3.40. C of V, which is the heat capacity, is equal to R divided by K minus 1. In this case, our needed value would be 1.986 divided by our molar mass of air, which is 28.97, divided by 1.4 minus 1. Our heat capacity is 0.171 BTUs per pound degree Rankine. Now, as we move into equation 3.40, you can see the work of the cycle is equal to mass times heat capacity, open bracket, T1 minus T2 plus T3 minus T4, which are all known values that we found earlier in our slide. You input values that we have already found previously and multiply across, and you should get 0.387 BTUs as the work per cycle. Now that we have this information, we can calculate the total work of the engine. One thing to note is that 2 revolution is equal to 1 cycle. So, as you see in our initial equation, work of the engine is equal to cylinders times RPM times work. As it is elongated and it's transformed into our wanted value, you see that 4 cylinders times 2800 divided by 2 cycles, due to the fact that 2 revolutions is 1 cycle, times our work, which is 0.387 BTUs per cycle, times 60 minutes per hour, times 1 horsepower, which is 2,545 BTUs per hour, which gives you our initial ending value of 51.093 horsepower. Last is the mean effective pressure, equation 9.1, or also known as MEP. It is equal to the net work for 1 cycle divided by displacement volume. As you can see in our problem, the work of the cycle divided by V1 minus V2, or in our case, work of the cycle divided by V1 open parenthesis 1 minus V2 divided by V1, which, as we have seen earlier in the problem, is 1/10. As you input your known values, you can see that 778 foot-pounds is a conversion for BTUs into our needed values. As you solve across, you can see that MEP is equal to 118.62 pound-force per inch squared. Now to review the equations. Equation 1, T2 divided by T1 is equal to V1 divided by V2 to the K minus 1, equation 9.6. Equation 2, P2 divided by P1 is equal to V1 divided by V2 to the K, equation 6.43. Number 3 is PV equals MRT, equation 3.33. Number 4, CV is equal to R divided by K minus 1, equation 3.47b. Number 5, work is equal to M times CV, open bracket, T1 minus T2 plus T3 minus T4, close bracket, equation 3.40. And 6, MEP is equal to the net work for 1 cycle divided by displacement volume, equation 9.1.